So these are all just kind of a review of things we've done in the last couple of weeks. Number one here, we're just multiplying. Remember, we combine the counts. So we have 7 times 3, which is 21. Then we combine each name separately. X to the 5th times x to the 3rd is x to the 8th. Y to the 7th times y to the 4th is y to the 11th. So we get 21, x to the 8th, y to the 11th. Number 2, we have same type of problem, just a little trickier. We have the negative for 1. We have negative 4 times 8, which is negative 32. Do each variable separately. We have a to the 2nd times a to the 5th is a to the 7th. Now we have a b to the 7th here, and there's no b in the second one. What does that mean? We just keep the b to the 7th. There's nothing to combine it with. And then the same with the c to the 3rd. There's nothing to combine with that, so it just stays c to the 3rd. So negative 32, a to the 7th, b to the 7th, c to the 3rd. Now down here for number 3, this isn't just 2 single-digit numbers anymore. We are multiplying a single-digit number by a 2-digit number. And if you recall, the way we did that was we distributed. So 8x to the 3rd times 4x squared is going to give us, perfect, 8 times 4 is 32, and x to the 3rd times x squared is x to the 5th. And 8x to the 3rd times a negative 9x. Perfect, negative 72x to the 4th. 8 times negative 9 is negative 72. X to the 3rd times x, we think of that as x to the 1, becomes x to the 4th. And then number 4. We see the parentheses, which tells us we should look there first. Is there anything to do inside there? No. So then we look to see what needs to be done to it, and it's multiplied by a negative 5y to the 3rd. Remember that symbol, that operation always goes with the number that comes after it. So it's going to be negative 5y to the 3rd times 4y to the 6th. Negative 5 times 4, negative 20. Y to the 3rd times y to the 6th, y to the 9th. And then we have the negative y to the 5y to the 3rd times a negative 3y to the 4th. Positive 15, y to the 7th, good. Negative 5 times negative 3 is a positive 15. Negative times the negative makes a positive. And y to the 3rd times y to the 4th is y to the 7th. Now we still have that 9y to the 7th up front, and that plus 8y to the 9th at the end. Are we done? No. We still have things we can combine. Now, I'm going to change the order here just a little bit. You would not be wrong if you didn't do this, but I'm going to do the y to the 9th first. I've got negative 20y to the 9th and positive 8y to the 9th. Negative 20 and positive 8 make negative 12. Very good. Y to the 9th. And now I have the 9y to the 7th and 15y to the 7th, which makes 24, y to the 7th. Good. The reason I switched the order there was I wanted to put the largest power of 9 first, or power of y first, the y to the 9th. It's not wrong if you don't do that. It's just kind of like a grammar thing. It's more correct if you put the largest power first. They're referred to as descending order, because if we look at place values in any number, like in the powers of 10, the decimal number system that we use, the larger powers of 10 come first. Same thing, your larger powers of the variable come first. Kind of like when we do multiple variables like this, it's always more appropriate to list them in alphabetical order. Again, if you don't put them in alphabetical order, it's not wrong. It's just kind of that grammar thing. One thing we've talked about a lot is the perimeter. If I give you a rectangle that has a length of 3x squared plus 7x and a width of 5x plus 12. I want you to write an expression for the perimeter. Remember, the perimeter is 2 times the length plus 2 times the width. What's going to go in here for the length? That'll be the 3x squared plus 7x. Plus 2 times the width. Well, what goes in for the width? The 5x plus 12. Now we do, if we left it like that, it would not be wrong. That is a perfectly good expression, but it's much better if we simplify it. We see that we have the parentheses. There's nothing to do inside either parentheses. So we'll distribute the 2 here. 2 times 3x squared is 6x squared. 2 times 7x, 14x. Then here we have 2 times 5x, 10x, positive 10x. And 2 times 12 is 24. And to finish that off, we should combine. We got positive 14x and positive 10x make positive 24x. Good. So that becomes 6x squared plus 24x plus 24. Any questions? Okay, well, today we're going to shift gears a little bit. By the way, for any of you that were not here on Monday, remember tomorrow is career day. So from 8 until like 4, there's high schools touring the building, so regular classes will not meet. So this class won't formally meet. There will actually probably be another group in here for career day. But if you guys have any questions, I will be in the building, most likely down in the broadband or telecommunications lab. So if you have any questions on anything, you can come find me down there. So anyway, our new material for today. I want to start out by talking about divisibility. Divisibility is simply if a number can divide into another number without remainder. For example, 12 is divisible by 3 because 12 divided by 3 is 4. There's no remainder, no decimal, no fraction. 27 is not divisible by 4 because if I divide 27 by 4, I get a 6 with a remainder of 3, or 6.75, or however you want to express it. So divisibility, we have to get a result that is a whole number or integer with no fraction, decimal, or remainder. How can you tell if a number is divisible by another number? Well, we have some divisibility rules. To tell, of course, everything is divisible by 1, so we don't really count 1. To tell if something's divisible by 2, what has to happen? An even number. And to specify an even number means the last digit is 2, 4, 6, 8, or 0. If the last digit of the number is 2, 4, 6, 8, or 0, it can be divided by 2. How about 3? How can you tell if a number is divisible by 3? Not necessarily, because 6 is divisible by 3. We call it sum of the digits. What that means, let's say we have a number like 5,922. So at first glance, you might not be able to tell whether it's divisible by 3, but if we look a little closer, we do 5 plus 9, what's that give us? 14 plus 2, 16 plus another 2, 18. Is 18 divisible by 3? Yes, so this 5,922 is divisible by 3. 4 has a rule, but it's really kind of complex. It's if the last 2 digits are divisible by 4. So what that means is if we have something like 327,948, all that matters there is the last 2 digits. Is 48 divisible by 4? Yeah, so if that were 48, 52, 56, anything that's divisible by 4 in the last 2 digits, the whole thing has to be divisible by 4. That one's not horribly useful because not too many of you have your multiples of 4 memorized up to 100, which is what that actually technically 96, but still. 5. How can you tell if something's divisible by 5? There you go. It ends in, or the last digit is 5 or 0. So again, some long number like that, 579,265, all that matters is that last digit. 6. 6 is another one that's a little more complex. A number is divisible by 6 if it is divisible by both 2 and 3. So like 5,922. Now we've already checked and we've certified it's divisible by 3. But really what I always check first is the 2, because the 2 is real easy. Is this divisible by 2? Yeah, the last digit's even. The last digit's 2. So then we check to see if it's divisible by 3, and we already did that above. So this is divisible by 6. 7, anybody know of a rule for 7? Neither do I, actually. There is not one that I know of for 7. If any of you can find one that works, let me know. 8 is another one kind of like 4 that's not terribly useful. It's the last 3 digits. So if I have something like 289,128, what matters is these last 3 digits. Is 128 divisible by 8? Well, it is, but again, most of you don't have your multiples of 8 memorized up to 982. Technically up to 1,000, basically. So that's not horribly useful. Now, I've mentioned a few of these that aren't horribly useful, like the 8 and the 4. How do we get around that? Well, if we're dividing them by anything, 8 and 4 can both be divided by 2, can't they? So we can just divide by 2 multiple times. In fact, I don't even ever really use that rule for 6, because I just divide by 2, and then I divide by 3, and I've divided out the 6. 9. The rule for 9 is the same as the rule for 3, actually. Sum of the digits. The difference is that the sum of the digits has to divide by 9. Well, 5,922, if I add up the digits, we already did this, they add up to 18. Is 18 divisible by 9? Yes, so then the whole thing is divisible by 9. Now, I do use that one occasionally, but again, If you want to divide by 9, you can just divide by 3 twice. You've divided by 9. 10 is the easy one. The last digit is a 0 always, yes. Now, as we go larger than this, there are some divisibility rules, but they get more and more complex as the numbers get larger, to the point where they're really not useful. Let me show you an example. 11. You don't need to write this down because I would never ask you to know it. I'm basically showing it to you to show you that it's not worth knowing. If I give you a number like 7, 2, 8, 5, 9, let's see what's that? I think that'll work. 728,596. What you do is you start with the first digit and you go every other digit. So I've got 7, 8, and 9. If I add those up, I get 24. Then I take the remaining digits, 2, 5, and 6. If I add those up, I get 13. If I subtract the smaller one from the larger one of those two totals, if I get either 0 or a number that's divisible by 11, then the whole number is divisible by 11. So this whole thing is divisible by 11. But again, that's a long process to try to figure that out. And with modern calculators, it's probably just as easy to punch that in and hit divided by 11. And if you don't get a remainder or a decimal, you know it's divisible by 11. You can see it comes out to a whole number, so you know it's divisible. Other numbers as we go larger, we have some divisibility rules, but they're not necessarily needed. Because we have two different types of numbers that we're going to talk about here. We're going to talk about prime and composite. We talked about the 4, the 6, and the 8, and the 9, where we didn't really need a divisibility rule for them because we just divide by smaller numbers. That's because those are what we call composite numbers. Composite numbers have smaller factors. By smaller factors, I mean numbers that divide into them, or numbers that can be multiplied together to make them. Prime numbers are divisible by only 1 and themselves. Remember we said we didn't count 1 as being a divisibility issue because anything can be divided by 1, so we don't count that. Factors are smaller numbers that make up those larger numbers. So obviously prime numbers have no factors because we don't count itself in 1. Composite numbers, of course, have factors, have smaller factors. So if I have the number 24, that has several sets of factor pairs. It might be 2 times 12, 3 times 8, 4 times 6. All of those are factor pairs for 24. Well, if I ask you to factor something, which set do I want? Which pair do I want? It can be confusing. So generally, when we ask somebody to factor something, what we really want them to do is prime factor. And what prime factor is we're breaking it up into the smallest possible pieces rather than just into a pair of factors. So for 24, prime factoring. What we would use, the tool we often use is called a factor tree. And what we're looking for is what's any number that divides into 24. Don't be shy. 2. So if we have 2, what is 24 divided by 2? 12, so there's 12 left over. Can 2 be divided by anything other than itself and 1? No, 2 is prime. So I'm going to circle that, indicating that we're done there on that branch. 12 can be split up, though. What's one thing that divides 12? 6. Very good. What is 12 divided by 6? 2, so there's 2 left over. Now that 6 can be split up further. The 2 is prime, so I'm going to circle it. What can 6 be split up into? 3 times 2. So what that's telling us is that 24 prime factors into 1, 2, 3, 2 times 2 times 2 times 3. And again, we usually do put them in order from smallest to largest. In fact, with what we know of powers and exponents, if we wanted to, we could shorten that up and write it as 2 to the power of 3 times 3 instead of 2 times 2 times 2. Depending on how we're using them, sometimes it's more convenient to have it in this exponential or power form. Sometimes it's more convenient just to have them listed out individually like that. Why do we care so much about factors? Well, because factors allow us to determine a couple of big things. One is they allow us to determine the greatest common factor. The greatest common factor is the largest number that is a factor of both. So obviously when we're looking at a greatest common factor, we're actually looking at two numbers. Now greatest common factor, you're going to see me write it as GCF from now on. You won't see me write out the whole phrase. The GCF of 18 and 45. Well, I could list out all of the factors of 18. 18 is divisible by 2, 3, 6, and 9. I could list out all the factors of 45. There's 3, 5, let's see here. 9 and 15, right? That's all of them for 45. If we look at that list, we can see the largest one that's in both lists is the 9. But could we have found that without having to make the complete list? We could by prime factoring. So we would prime factor the 18. I might do that as 3 times 6. 3 is prime. 6 is going to split into 2 times 3. So 18 is 2 times 3 times 3. If I do the same thing now for the 45, well, it ends in a 5, so I take out a 5. 45 divided by 5 is 9. 5 is prime, so I'm going to circle it. 9 can split into 3 times 3. Those are both prime. So 45 is 3 times 3 times 5. The greatest common factor is a combination of all of the common factors. I have 3 that's in both of them, and I have another 3 that's in both of them. What's 3 times 3? 9. That's my greatest common factor. In your notes, I'm going to have you see if you guys can find the greatest common factor of 24 and 30. I'll give you a second to do that. Is anybody having problems doing the factor tree and prime factoring? So that's the best place to start. No? Okay, good. So 24 factors into 2 times 2 times 2 times 3. 30 is 2 times 3 times 5. What do they have in common? They have a 2 and they have a 3. 2 times 3 is 6. So 6 is their greatest common factor. Different from a factor, we have a multiple. A multiple is actually all the numbers that that number is a factor of. So example, the multiples of 4 would be 8, 12, 16, 20, 24. Those are all the numbers that the 4 can divide into. So it's basically going the opposite direction. Factors are smaller than the number. Factors go into the number. Multiples are larger than the number. The number goes into its multiples. Well, we look at something called the least common multiple. Least means the smallest of those numbers. Again, we're looking at two different numbers and finding that smallest multiple that's in common. Let's say we're looking at 12 and 8. We could make a list like we did up here and just find the smallest number that's in both lists. But let's stick with our factoring. 12 is 2 times 2 times 3. 18 is 2 times 3 times 3. Now, just like we did with the greatest common factor, we still start out with the ones that are in common, but that's not where we're going to stop. So we've got a 2 in common, they've got a 3 in common. From there, we look at the ones that are not in common, the ones that are left over. The 12 has an extra 2 in it, doesn't it? So we put an extra 2 down there. My 1 disappeared on my 18, didn't it? There we go. Probably a little less confusing with that 1 there. So we put a 2 down there. Now they both have a 2 in common. What's the 18 have that the 12 doesn't? A 3. So we put the 3 up there. Now they both have a 3 in common. Now they both have all of the same common factors, which means they'll be the same. So this is 12 times 3, which is 36. This is 18 times 2, which is 36. 36 is the least common multiple of 12 and 18. Now that is something we'll look at more as we go on. For right now, the greatest common factor is kind of our most important concept. But the reason we're talking about factors so much is we're going to be getting into fractions now. And understanding fractions, a lot of what we do with fractions involves factors. But before we get too far into it, let's talk about how our fractions are set up again. We had a fraction like 3/4. Remember, we talked back in the first couple of days of class that fraction is a single number with 2 parts. The 3 is a count. We have 3 of something here. Just like having 3 inches or 3 cows or 3 pounds, there's 3 of something here. And the 4 is a name. So that's like the inches or the cows. The name here is a 4th. So the first thing we need to do is to define what does it mean to have a name of a 4th. The simplest way to deal with that is to go back to the old elementary school illustration of a pie or a pizza. That 4th, that 4 means that whole object is divided into 4 pieces. So we can actually view it one of 2 ways. Either every whole object is divided into 4 equal pieces, or the other way you could look at it is it takes 4 of those pieces to make a whole object. The 3 means that we have 3 pieces. So we don't quite have a whole object at this point. Now, one of the first skills we need to be able to do with fractions is we need to be able to rename them. Now, we had that example back on the first day of, I think it was like 1/4 plus 3/5 or something like that. We couldn't add those because they have different names. But we're going to need to change their name so that we can add them. One of the ways we can change the name of a fraction using this illustration, probably the simplest way to do it is to just take each of those slices and cut them into equal slices. Now I'm just picking the number 3 to use. I'm cutting each slice into 3 equal slices. Pretend these are equal. Now, how many slices does it take? How many pieces does it take to make that whole object? There's 12. We had 4. We cut each of them into 3 equal pieces, so 4 times 3 is 12. How many pieces do we have there in the yellow? 9. We had 3. We multiplied. We cut them each into 3 pieces. 3 times 3 is 9. Do we have any more or less pizza than we did before? No, it's the exact same amount. 9/12 and 3/4 are the exact same amount. It just looks different. The reason that that amount didn't change is because of what we did right here. We multiplied by 3 over 3. The bottom 3 is telling us it takes 3 pieces to make a whole object. The top 3 is telling us we have 3 pieces. In other words, we have one whole object. When we multiply something by 1, what does it do to its value? Nothing. It doesn't change it, right? It stays the same value. So that concept of multiplying by 1 is called a unity fraction. That unity fraction concept gets used a lot in math. As long as we have 2 things that are equivalent, we can use it for making conversions. That's how we do our measurement conversions. If you were in a medical field, that's how you do your dosage calculations using a unity fraction and equivalence. It's just a very, very powerful tool. Now here, as I said, we just picked that value of 3 to divide each slice into 3 pieces. In practice, most often, we are going to have to figure out what that number is. For example, let's say we have the fraction 2/5, and I want to change it into 20ths. I need to figure out what I am going to multiply both of them by. Well, to do that, what do I multiply a 5 by to turn it into a 20? 4. So what do I have to do to the 2? Times 4. Make 8. 8 20ths is equivalent to 2/5. So really the hardest part there is going to be figuring out what you're changing them into. Once you have that, you just have to figure out what you have to multiply by to get it there. Now, we can change the name by finding similar fractions here by multiplying the top and bottom. Again, that's the same value, it just looks different. But we sometimes want to go back the other direction, which is called simplifying. Sometimes called reducing. I don't like the term reducing because it implies you're making the value smaller. We're not. The value is staying the same. We're just making each of the pieces smaller. But here, we change this by multiplying by 4 on top and bottom. If I divide by 4 on top and bottom, what's 8 divided by 4? 2. What's 20 divided by 4? 5. And we've already shown that 2/5 is equivalent to 8 20ths. So we can reduce that fraction by the same amount. Now here, we had done the multiplication, so we knew what to divide by. The tricky part is often figuring out what to divide by. We have a fraction like 48/60ths. It's awful difficult to visualize that it takes 60 pieces to make a whole object, and we have 48 of them. In fact, the human brain struggles to visualize more than 13 objects. 7 to 13 objects is the typical. We've always been taught that to reduce that, we have to come up with the largest number. That would be the greatest common factor. That's not necessarily true. Can anybody look at those and tell me what the greatest common factor is? 12 would be it. 6 is close. What if we didn't see the 12? What if we went with the 6? Well, 48 divided by 6 is 8. 60 divided by 6 is 10. That's still equivalent, but we'll look at it now when we see that we can still divide both of those by 2. Get to 4/5. If we divided by 12 right away, we would have got the 4/5 in one step. But we're still going to get there. It's just a couple more steps is all. We can also run into things like this. 44/7. That 7 on bottom in the denominator is telling us it takes 7 pieces to make a whole object. Well, the numerator is saying we've got 44 pieces. We have more than enough pieces to make, well, several whole objects in this case. So to figure out how many whole objects, we've got to figure out how many times can we take 7 out of 44. Well, if we divide this out in our calculator, 44 divided by 7, our calculator is going to give us something like 6.2857143 approximately. What's that tell us? Well, it tells us we can get 7 out of there 6 times, and that there's some pieces left over. The better way to do this, to figure out how many of those pieces are left over, is to do a long division with a remainder. 7 goes into 44 6 times. What is 6 times 7? 42. That means there's 2 pieces left over. So there's 2 of those 7ths left over. So 44/7 is 6 2/7. This is what we call an improper fraction. Now, it's sometimes just called a top-heavy fraction, which is probably a better name for it. Improper implies there's something wrong with it, and there really is not anything wrong with it. In fact, there will be times where we prefer to have the fraction in that form. It's just we don't like having the numerator bigger than the denominator. This is what's called a mixed number. And it's called a mixed number because it mixes whole numbers and fractions together. Now here we went from an improper fraction to a mixed number. What if we want to go back the other direction? Well, up here we took those pieces and we combined them to make whole objects. Down here we've got to do the opposite. We've got to take the whole object and break it back into pieces. So how do we know how many pieces each of these 6 whole objects has in it? The denominator tells us. It's telling us that in this case, each whole object is 7 pieces. So to get the 6 into pieces, we do 6 times 7, which is 42. That's 6 whole objects is 42 pieces. Is that all the pieces we have? No, we already had 2 of them. So 2 plus the 42 is 44/7. We will have more time next week to work with fractions. There is a new homework that is due next Monday, and there is a new quiz due tomorrow, due Thursday at 11:59 p.m. Tomorrow for career day, the computer lab should all be open, so you can come in and use computers or whatever in the school if you want to. If you're in programs, your program instructors may have other requirements that they want you to do for the day as well. So, anybody have any questions? Okay, like I said, I will be in the building tomorrow. I'll be down at the telecom or broadband program. If you have any questions, please find me. Otherwise, we'll see you on Monday.